Let's look at graphing trig functions in particular. So our sine curve, we'll recall our basic sine curve has an amplitude that goes up to 1 and down to -1. And when I'm drawing my sine curves, I tend to mark off the boundary values. So every 90 degrees, or if I'm using radians, every pi on 2. The sine curve, of course, starts at the origin and then moves up to the amplitude. And that pattern, which looks like a zigzag, continues. So we'll go down and up and down and up and then back the other way as well. But of course we don't draw a zigzag, we have a nice smooth curve. So there's the basic sine curve. The domain's all real x, of course. The range, as I mentioned, -1 to 1. So if I was to generalise this to take into account all different types of shifting, so a sine bx plus c. Now the period of a sine curve, or any curve for that matter, is how long it takes for the curve to repeat the pattern. And when we repeat the pattern, we must be going in the same direction. So for our basic sine curve, it's 2 pi or 360 degrees it takes to repeat the pattern. Well, when we generalise it, it always turns out to be 2 pi divided by whatever the coefficient of b is. Because remember, b was stretching or contracting the graph, so it's going to change the period. The amplitude is the distance from the axis of the trig curve to the peak, or the trough for that matter. In our basic one, it is 1, but it'll always turn out to be the coefficient of the sine function. Because again, if we think of it from our stretching, contracting way, that a I could rewrite as y over a, and then that changes the y value. Now, I mean, this is not a technical thing, it's just how I work out my divisions. I go, well, whatever my period works out to be, whatever that is, I'll divide by 4, and that's what I'll mark off, because that's where all those key features, those boundary points, will become. So really, I could draw the same sine curve for every curve and just change the labelling. As long as there's only one on the axis, of course. Once there's more than one, well, all right, we have to do it differently. And phase. Phase is a fancy way of saying the shift of the graph. So, of course, the shift happens when it's grouped with the x. So if I was to factorise this, then it would become c over b. Is the shift, or the technical term, phase. It is, of course, an odd function, so we see our rotational symmetry there. And so sine of minus x is equal to minus sine x. Okay, so let's try and draw this one. We've got 5 sine 9x minus pi on 2. How would I approach this? Well, the first thing I do is work out the period, so I know how am I going to mark off my axes. So it'll be 2 pi divided by the coefficient of x, which is 9 for this one. The amplitude, so for the y-axis, will go up to 5, down to -5. So okay, I'm going to mark off my divisions. When I'm labelling, I'll label them every pi on 18 will be the label. So my period divided by 4. And in this case, there is a shift happening. It'll be pi on 18. Is the shift. Again, what would make that equal to 0? What would make 9x minus pi on 2 equal to 0? It would be pi on 18 that would make that equal to 0. All right, so let's draw it in. Axes, amplitude. Now, mark off my divisions, but every pi on 18, but I'm being a little bit lazy there and only labelling every second one. So that's pi on 9. Now, normally I would start at the origin, and I'd say, okay, origin for the sine curve, but this one's shifted pi on 18 to the right. So my first point I'm going to mark in is at pi on 18. Then I know the pattern of the sine curve. It goes up to the amplitude. So at pi on 9, I'll have up at 5. And then that pattern, that zigzaggy pattern, will continue. So we'll go down and then back the other way, and I'll draw in my sine curve. Now, just something to note about this. If they had said draw it for the domain of minus pi on 9 to 2 pi on 9, I should stop at those points. Okay, cosine curve. Well, the cosine curve and the sine curve are the same curve. Because remember, co stands for the complement of sine. So basically, it's just a shift of the sine curve. So the same things we should see. If I generalize it, a cos bx plus c, once again, the period would be 2 pi and b. That's not going to change. The amplitude will be a, not going to change. I'll mark off my divisions every period on 4. Yep. Phase is still c on b. In this case, you remember a cosine curve is an even function. So we should see symmetry in the y-axis. So let's do minus 4 cos x on 8 plus pi plus 2. Let's go crazy. Okay. Work out the period. So it'll be 2 pi divided by an eighth, 16 pi. Amplitude. Amplitude's always a positive number. So I suppose my formula before where I said it's A, it's probably more correct to say it's the absolute value of A. So 4 is the amplitude. I'll mark off my divisions every 4 pi. The shift in this case is going to be 8 pi, it'll go to the left, but also we've got to shift 2 up. Well, if it's 2 up, what I'm going to do, notice I've just drawn a dotted line in there, because my axis of my cosine curve is not going to be the x-axis. So I just need that reference line to know where I'm going to plot those points. So that'll be at 2, it's been shifted up 2. And if the amplitude's 4, then I'll be going up to 6 and down to negative 2. Now, normally, I would start a cosine curve at the amplitude. If you think of your basic cosine curve, cosine of naught is 1, so you start at the amplitude. But what's happening with this one? So shifted 8 pi to the left, 2 up, but then it's upside down as well because of the negative. So I will end up plotting it down here at negative 2. So minus 8 pi, negative 2. So normally I'd start at the amplitude, but it's a negative 1. So it's still at the amplitude, but at the trough rather than the peak for this one. The cosine curve, that pattern, we then go to the axis, and again that zigzag pattern will continue. So, whoop, there's our cosine curve. All right, tangent. Well, tangent is a little bit different. So there's a tan bx plus c. Period for a tan curve is only 180 degrees, or pi. So when I generalise it, it'll become pi divided by b instead of 2 pi divided by b. And the key divisions now, I only have to divide by 2 for that. So it's still on our basic one every 90 degrees, but so whatever the period is divided by 2. The phase is still the same, of course, it's c over b. And if you recall, the tan function is an odd function, so it should have rotational symmetry. What the heck? Let's do E tan pi x minus 2 pi. By the way, notice what piece of information I didn't bother with the tan curve. What's missing there?
Amplitude.
Yeah. I didn't bother with amplitude because a tan curve doesn't have an amplitude. Remember, it goes all the way up to minus infinity, all the way down. So we don't really talk about amplitude with tan curves. That's why, really, I could put any number out the front I like. If I don't have a scale on my y-axis, I mean, they're all the same. So let's put E there. So period is 1. So I'm going to mark my divisions every half. And we've shifted, it ends up being 2 to the right. Again, if I was to solve that pi x minus 2 pi, what do I get? I get x is 2. Okay, so let's draw the axes in. Again, I'm not going to worry about the y-axis. So x-axis, and we're marking these off every half. So every second one is an integer. The pattern of the tan curve. Well, tan of 0 is 0. So it's another one where normally we start at the origin. But this one is shifted 2 to the right. So I'll start over there at 2. Now the key features on a tan curve, if you recall, it goes x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote. So let's draw that in. There's the asymptote on the right-hand side. We'll go back on the left-hand side, and that pattern repeats. And our tan curve, whoop, there's one branch of it. Remember, you're not drawing in y equals x cubed. There's not a horizontal tangent here, it actually goes through the axis at 45 degrees. It should go through at 45. Okay. And then that repeats in each of those sections. So there's y equals e tan pi x minus 2 pi. In fact, the shift 2 to the right had zero effect on it if you look at it, because the period was 1, so it was repeating then anyway. It's exactly the same as if it had just been e tan pi x. So 3j is just drawing up different trig graphs.